Hi, everyone. My name is Lyle Tavernier, speaking to you from NASA's Jet Propulsion Laboratory here in Southern California. Joining me today is my friend and colleague, Brandon Rodriguez, and we are going to be talking about water filtration, and we're even going to be taking some time today to build our own water filtration devices. But before we do that, we're going to talk a little bit about water on Earth, how it's used, and some other things that we might want to consider as we're thinking about water and our use of water. So Brandon, I know you had a couple things that you wanted to share.
Yeah, absolutely. Thanks, Lyle. I think before we really get started into engineering our device, we probably want to know a little bit more about why it is that there's so much importance around water and protecting this resource. We maybe have the privilege of seeing water around us all the time, but being able to access clean water and be able to effectively recycle used or wastewater to make it into clean drinkable water is certainly a pretty technologically difficult concept. This has become much more pressing over time, as you guys can imagine, due to, of course, what we're seeing in changing climate and more extreme weather. Here at NASA, even though I think many people think of NASA as looking outwards into space, we actually have a very large fleet of Earth orbiting missions. So a lot of technology is actually built and designed and is continuously operating, exploring the health of our planet, tracking all sorts of things from the gases in our atmosphere to the sea level change to the temperature of those oceans. So for example, when we look at how we can track climate change over time, thinking about sea level rise is one of those most critical concepts. So you may or may not be close to a coast, but nonetheless, the average height of the ocean is increasing and encroaching on the beaches that we feel out here in California. Now, of course, if you actually are part of a ocean community, somewhere living in the Pacific Islands, you might feel this impact even more so. So just tracking the sea level rise over time is a critical indicator for how our climate is changing. Another really important way that we track this is actually with ocean temperature. Now, again, if you think about perhaps your original chemistry class, you might have learned that warm things expand. So in fact, a decent amount of the ocean level rise that we're seeing comes not from just melting ice, but also from the fact that the oceans are getting warmer. And because they're getting warmer, the temperature profile of the oceans are changing dramatically. So it's expanding, the concentration and density of that water and the things therein is changing. And of course, this is going to impact marine life dramatically as well, thinking about things like migration patterns, the depth at which they swim, and so forth. So for us, this changes things like fishing and availability of marine resources. But from an ecosystem perspective as well, we kind of have to be concerned about what impact we're having on our planet. So these are some of the ways that NASA monitors effectively how climate is changing, thanks to these orbiting satellites and missions. Now, we've used the word climate several times so far, but this is really only one of the two ways that we kind of have a feel for how climate is changing. And a really good way to differentiate climate change, which is a longer term problem, versus extreme weather, which is something you would see kind of in the short term, is to kind of take a look at how events have changed in your regionality. So again, out here in California, we don't have a lot of rainfall, although that kind of changed in the last few weeks. So California got pummeled by 6 weeks of rain to start off the year. But I used to live in Texas. I lived in Houston, and I took two photos that I thought you guys would appreciate. The first one is the highway looking from north to south of downtown Houston. And then I went back and took another photo. I tried to line it up as best I could. This was immediately after Hurricane Harvey. So this was 12 feet of water all of a sudden just dropped on to Houston, Texas. Now, this was, obviously a devastating hurricane. And this is the type of extreme weather you might see if you live in Texas. However, not long after, I moved out to Los Angeles, where extreme weather looked very, very different for me. And having been used to seeing a lot of rain, all of a sudden I was seeing drought and wildfire. So if you can see here, effectively the bottom left picture is a fire coming down the mountains towards Glendale, where I live. So, all of a sudden we became, kind of thrust into the very different ways that we see weather. And here in California, where agriculture is so important, drought can be a really, really serious impact, because if we can't make the food and crops that get spread across the United States, then how is it that we're going to have a sustainable and reliable food source? So both in climate and in weather, we really have to be very, very careful about measuring, noting our impact, and thinking about solutions. So with that in mind, maybe we can switch to Lyle about how it is that we protect water, both in terms of a large scale here on Earth, as well as from a technological standpoint.
Thanks, Brandon. So one of the things that came to mind as you were talking was all the rain that we had here in Los Angeles over the last several weeks, and I guess a few months, really going back to January. And when it rains in Southern California, we have such a huge surface area that is just covered with concrete and asphalt. And it's important to sort of get that water off of those roadways and off of those surfaces in a safe way to protect people from flooding and things like that. But that is a lot of water. A single rainstorm, it's estimated that somewhere around 6 trillion gallons of water get dropped on the Los Angeles area and then are funneled into different channels into the Los Angeles River and then are dumped out into the ocean. So when you're in a place that has had years of drought like California has, and you hear about 6 trillion gallons of water being funneled off into the ocean, there are a lot of people who think, well, couldn't we use some of that water? And there are a lot of people who think, yes, we could, but there are some things that we have to consider. And one of those things is the contamination of that water. As it falls to the ground and hits the surface, there's a lot of not just dirt, but there's a lot of pollutants on the ground that get captured and mixed into that water. And so we can't just go to the LA River and scoop up a cup of that water and have some of that to water our plants, or certainly not for drinking and brushing our teeth or anything like that. But how can we capture some of that water? How can we clean it? How can we use it to recharge some of our depleted water from underground, called groundwater, that we use for things like agriculture and water supplies for our household needs? So there are a lot of ways to think about how we can use and capture that water, not just here on Earth, but also in space. So water usage is very important for astronauts. I mean, we've got water bottles here that we were drinking from earlier, and that doesn't change when you go into space. You need water, just like you do here on Earth. In fact, you can go a few days without food and be okay, but you can't go a few days without water and still be okay. But because the International Space Station is so far away and so difficult to get to, orbiting around Earth, we can't just send water up every couple of days. And so one of the things that we have to think about is how can we recycle and clean the water that we have that's up there already. And I'm going to put a picture up here of what is called the ECLSS unit. And I have to think about what ECLSS stands for, the Environmental Control Life Support System. I'm pretty sure that's what it stands for.
Sounds very convincing.
And it does a lot on the International Space Station. Now, what you're seeing on the screen is not in space. This is a version or a model that we built here on Earth so that we have a working version and can test and work on things here in case any repairs need to be done in space. We can try it out here. But in addition to things like cleaning the air, ECLSS also cleans the water. So when astronauts are brushing their teeth, they will spit it into a little tube. When they are, let me think about some other instances. When they are maybe washing their face, they can rinse that washcloth out and collect some of that water. But one of the big ones that people don't think about is when they go to the bathroom. So it's a big, very popular question. How do astronauts go to the bathroom in space? But most people don't think about how do astronauts drink water in space. And there is a connection between those two questions, and it has to do with filtration and the ECLSS system and taking what would otherwise be contaminated water and turning it into clean, drinkable water. So it's not just useful for us here on Earth, but it's also something that can be done in space and has to be done in space. Otherwise, you simply cannot have long-term missions on the International Space Station or the kinds of missions that we want to send to Mars, where humans would be traveling for 8 months to get there, be on the surface for, a few months, perhaps several months, and then 8 months coming home. We just can't pack that much water into a spacecraft on its way to Mars. And so we practice these things on the International Space Station to get good at them and make sure that those technologies work. And astronauts have been doing this, recycling their water for, I think it's been 20 years that we've had astronauts on the space station. So for quite a long time. So that's actually a question I like to ask people. I should have done this first. I should have asked, how many of you want to be an astronaut? And then after I tell the story about where their drinking water comes from, I ask that question again, and not as many hands go up. But it is something to think about and something to be aware of, because we need water filtration here on Earth as well, not just in space. So that sort of leads into the activity that we're going to talk about today. You want to talk a little bit about it?
Yeah, absolutely. So I'm hoping that you guys can follow along with us, and we have several materials here. Everyone will have different materials at home or in your classroom, and that's totally fine. But the one key thing that you need to have is a water bottle. So a used water bottle like so. We're going to build our own Eclipse system, if you will. The first step that we're going to kind of go through to make that happen is what we're going to do is we're going to cut with a pair of scissors. And you can kind of cut effectively your bottle really anywhere you like, maybe around halfway up, right? So I'm going to do that quickly. It's going to be a little crunchy.
And I'm going to cut mine a little further down just to try something different. I don't know exactly what Brandon's plans are for his filtration device, but I'm going to cut mine a little lower and I'll make the same crunchy sound. Oh boy. Well, splashing a little water. Okay.
Well crunched, yeah. And what you guys would like to do here, if possible, is we're going to build a filtration system where we effectively cap this here and place like such. So what we haven't done is figured out what materials will go in here to kind of construct a layered system capable of filtering out some very, very polluted water. But to do so, we probably need to go through a few things first. Again, everyone will have something different at home, and that's totally fine. We have things like macaroni shells, some cotton balls. We have some coffee filters. And I think
I've got a little aquarium sand here.
Mm-hmm.
Do we have aquarium gravel too? I thought, nope, maybe just sand. All right, so little rocks basically.
Yeah, and I mean, again, you can have this and more or less. Again, we don't know yet what is the best combination. But I do find the most helpful thing is either taking a coffee filter or perhaps a strip of cheesecloth like so, and using that to hold all of your materials in your top portion of the bottle. So what I'm going to do here is just kind of put this cheesecloth in and then take a rubber band and just like secure my cheesecloth to the bottom. Like so.
Since Brandon's using cheesecloth, I'm going to switch it up just a little. I'm going to use a coffee filter, but I'm going to do the same thing. I'm going to put this rubber band on and really just try to keep everything that I put in from falling out. So now I'm ready to build my filter.
Perfect.
Okay.
So at this point, maybe we should kind of indicate the challenge. And again, I'm hoping that if you are following along at home, your parent or teacher has effectively pre-prepared some very, very disgusting polluted water, right? So this is the patented JPL brand of disgusting mix of gross water that we put together for you.
And if you haven't made this already, or you don't have it, and you don't know how to make the disgusting water, there are instructions on the website, and that link should have gone out to you in an email, or when you saw the event page, actually, the link was on there too. So you can make your very own disgusting water.
So I think what we'll do is just take a few minutes to kind of maybe make a first pass prototype. And I'm looking at our materials here, and I'm thinking to myself, if I have this water, which again, by all appearances, it's brown, it looks kind of cloudy.
And I can hear a little like there's something in there moving around. It's
Mm.
not just water. It sounds kind of like gravelly or I don't know, sandy in there. So that's something I'm thinking about too. What could maybe help stop those types of things from getting through?
So I'm going to go ahead and, really just kind of take a first guess. And I'm going to put some of these macaroni pieces in here in hopes to kind of maybe capture some of that larger pieces.
And I'm going to start, I'm thinking about aquariums, and I used to have some fish, and I'm thinking about how the sand got pretty disgusting at the bottom. So maybe it was capturing some of the nastiness that was forming in the water. So I'm going to start with some of this aquarium sand. Again, I like that Brandon mentioned this is just our first pass. We're going to filter this and see how it goes and change it if it doesn't do as well as we want it to.
Yeah, and very unclear. You saw we both kind of just poured a little bit amount. So is that a lot or a little? Do we have more than we need or not enough? Unclear at this point, but this is good engineering, is trying to understand how each variable kind of lends to a certain result. I believe that looking at this, even though Lyle, I think, is correct, that there are some larger pieces in here, I think there's also some more finer material that would be difficult to remove. So I'm going to go ahead and put some of these cotton balls in here in hopes of like catching it. And I want to kind of pack it in, I think, a little bit so that it can't just run past it.
I like your thinking. I'm going to do the same. So we're both using cotton balls, but I'm curious because underneath, you can kind of see mine a little bit. I'm going to have this sand, and underneath Brandon's cotton balls, he's going to have the macaroni. And you know what? I made mine a little bit too tall because now I can't reach in. So I'm going to poke these down with a pencil. But there we go.
Now Lyle's got me thinking, maybe I should put some gravel on the top of mine, and then I'll have effectively his upside down.
So this is interesting because I was thinking I'm going to put macaroni at the end. So we will effectively have made reverse versions of each other.
How interesting. Oh,
all right. Here's the macaroni.
Nice. Okay, so I've got a nice, level that out a little bit. Oh,
okay. Interesting.
I like that you made yours a little longer. You cut further down so that you have a little bit more room for the liquid to get poured in. Whereas I don't have a lot of space to pour my dirty water in. So that's going to be a little bit of a challenge for me.
Yeah. I do like that I have more room, but I also have a smaller container at the bottom, so I can't fill this up. Otherwise, when it filters through, it's going to overflow. So I've got to kind of keep in mind how much space I have for water and make sure I don't pour. Okay. I kind of have a sense now.
Yeah. That's definitely a good one. And we don't want to spill all over the TV studio.
Yeah. I probably wouldn't be very happy about that.
What do you think? Anything else you want to add?
Let's see. Yeah, why not? I'm going to take one coffee filter just because I have it here.
Ooh.
If I can get it in here the way I want it to,
That's
going to sort of provide an initial filter to just get rid of a lot of the stuff maybe I don't want in there. I've got to be careful to get it shaped right so that the water can actually get in and pass through, but I think that's pretty good.
And now we're at another interesting impasse here because I don't want to add the coffee filter, but I know that if I don't, we'll have introduced a second variable. Right now, we only have one variable, which is the order of our materials. So I want to be careful that if I really do want to understand which filter is best and what effect it has, that I only change one thing at a time. So out of good scientific practice here, I'm going to put the coffee filter in, and then we'll have exactly only one difference in between our two filters.
Oh, I like that comparison. Yeah. I didn't mean to make you change your design, but I do like your thinking.
All in the name of science. All right, so I'm going to try to, I don't have as much room, but maybe I can do a little cup like this.
All right. And as we're doing this, you may be following along as well. Keep in mind that once we do this, we'll take a few questions as well. So start thinking about those questions you might have about water filtration, water resources, studying water from space, and things like that. So Brandon, do you want to pour into yours first?
Yeah,
and
let's do it.
I'll pour into mine. So I know it's off camera. I can confirm for anyone who may be questioning what's going on off screen. He is in fact pouring the water into his container or into his filtration. And I do see some nasty floaty things in there. So
boy, that does not look good. I can tell
Ooh,
pretty quickly, guys. This prototype is not going to be the final design, not the best one. I'm looking at my design here, and I can see first of all, the fluid went through very quickly. That's my first note. So it's already almost completely through the filter. I just have a slow drip now, but almost everything I poured is now in the bottom. It might be difficult for you guys to see. It's clearly still gross, clearly still brown. But it doesn't look like it has a bunch of floating stuff in it. I think we filtered a lot of the physical solids out, but still nowhere near ready to drink. That's for sure.
So mine is still dripping. It's going slowly. So in terms of Brandon's noticing his went through quickly, mine is dripping about 2 drips every second. So there's actually still quite a bit up in the very top section. And I don't know if that's because of the structure or the order, because again, we have the same types of things, but we didn't measure out exactly how much we were putting in. So that could have something to do with it as well. But I think mine is I mean, I would not drink it, but I think it's ever so slightly clearer, less brown than Brandon's. Now that may change as it starts to fill up because again, it's not a whole lot in here. But it definitely filtered, both of ours filtered some of the big debris out. So,
Yes, most
so that's a
definitely.
start. Yeah, I'll let this set for a minute because there is still some water up at the top filtering through.
As you guys are doing yours, you might kind of think about other parameters that would maybe reflect on success or failure for your filters. So right now, we've really only talked about the color at the end. And clearly we both did not succeed, and that's okay. But is that the only thing that we care about? Well, you kind of heard us mention the rate, right? So by what degree is it actually coming through? So if mine comes through faster, well, that's actually good to know, right? Maybe I can get more water quicker. But you might say, no, I don't want, very disgusting water quickly. I want drinking water, even if it's a little slower. So maybe you could use something like mine for watering crops, whereas Lyle's filter would be better for astronauts to be drinking on the ISS.
And that rate is a good thing to think about in sort of the opposite direction too. Maybe I want a slower filter because it's going to have more time to filter out some of those contaminants, but I also want to make sure that I have enough water to survive. If I get 1 ounce of water per day from my filter because it's dripping so slowly, that's not going to be enough. So there's a balance between how much water am I getting and how clean it is versus getting a lot really quickly.
Lyle, I noticed you also kind of sniffing at yours. What was that?
Yeah, we talked about color as sort of an obvious indicator, but I have spent a lot of times outdoors and I have come across water that's been sitting around, and I definitely don't want to drink that. Even if my water bottle is running low, I'm not going to fill it up with that. And sometimes it's the color, but sometimes it's the smell that really clues me into just how contaminated the water is. And I was just kind of smelling to see if there was a difference between what was on top versus what has made it all the way through. And I probably should have smelled here. Ugh. Because I'm smelling some of my filtration device up here. And I would say I actually got some of the smell out.
Really?
Yeah,
Nice.
It doesn't smell as bad as it does in the container here.
Interesting.
Yeah.
Well, Lyle, you may or may not be surprised to know that when I made this disgusting water, I actually introduced an extra complication, which was I added a little bit of vinegar as well. So now, of course, I had never expected that Lyle would drink it, and only to find out that he had been drinking vinegar. But I did this because I wanted to highlight that even though we might have removed some of the color from the dirt, there are still other chemicals that perhaps we can't see with the naked eye that would absolutely render this water undrinkable. So for you guys as well, if you have access to it in your science classroom, things like little pH paper strips can be used to test your water to see, is it very acidic or very basic, or is it neutral? Water has a pH of 7. Or if you don't have a classroom, if you're at home, little things like testing water strips that you can get from the hardware store can also be used to take that same measurement.
That's an interesting point about the things you can't really see. And I don't smell the vinegar that you put in here because it's such a small amount. You don't need a lot of something to contaminate water. And I was thinking, as I mentioned, coming across a pond or something like that while I'm hiking, there are also unseen microbes that you can't see. The water could look very, very clear, and there could still be microbes that could make you very, very sick. So that's another thing. And in fact, on the International Space Station, they add a small amount of iodine to the water after they filter it to get rid of any potential bacterial contamination too. So lots of things to think about. Still going slow. How are we looking? I think mine is a little bit.
I'm inclined to agree. I think Lyle's is a little bit more clear than mine. So maybe just the order or the relative differences in the amount that we put in made a difference.
Yeah. Well, this was fun. I hope that you are able to make some of these as well. And again, we just put some things together. You don't necessarily have to use these same materials. Kind of think about what you have around the house or the classroom that you might be able to use to make your own filter, and see how you do. I've actually seen people do such good jobs creating their filters that the water looks pretty clear. Again, I wouldn't drink it because I know what's in here, and I know there's nothing that got rid of some of the potential bacterial contaminants, but color-wise and smell-wise, I've seen some pretty good filters built with these materials.
Awesome. And, again, teachers watching, please feel free to introduce as many other complexities to this as you'd like. You can change what the dirty water looks like. You can introduce a cost associated with each of the materials so that students have a budget and can't just toss things in like we did. So you can see who can make the best filter on a certain amount of dollars, right? Introduce kind of an economics factor as well, because that certainly is a real world factor for doing this in industrial applications too.
Absolutely. So I'm gonna say, if you've got some questions now, you can start putting them into the chat. You can send them either directly to me or to Brandon. We'll see them pop up here. And one of the questions that came up was about where we can actually find out about rainfall, like how much rain is actually falling and how much is flowing through some of these rivers. And NOAA, the National Oceanographic and Atmospheric Association, they have a lot of great websites that have information about rainfall, about the flowing of rivers, how much water is flowing through different rivers. Here in California, the state does a really good job of monitoring rainfall all over the state as well. So there are a lot of organizations through the state that capture some of that data too. And you can kind of look at what it's like every month and year over year to see how maybe this January compared to January of 2022 or 2021.
Awesome.
All right, let's see. Here comes a question.
Yeah, so April's asking, would it be good to rerun the water a second or a third time through the same filter? And that's an excellent question. Absolutely. You can imagine that perhaps we could build a device that does exactly that, that actually cycles through a couple times. And I really encourage you to actually try this. This introduces a ton of new parameters. For example, you could take your dirty water, like you saw mine was not so good, but what if I went and, just as you're asking, introduce this a second time? Well, we could see. Maybe we can kind of run this very quickly. But you could even go further. If I had multiple devices in series, maybe I could have one that's just macaroni. Maybe I could have one and then rerun it just through sand or something like that. So yeah, the world is totally your oyster. Go nuts and see exactly what type of combination or number of cycles works for you.
Yeah, I'd be interested in that sort of adjustment of this experiment, because as we're putting it through the sand or the macaroni or the filters, there's probably a limit to how much some of those things can filter out. And when they reach that limit, they're not going to be doing a very good job. I know that when I have my water filter at home, it gives me a little reminder every 2 months that says, hey, you are supposed to change your filter. And that's probably because it's getting to a point where it's not going to be able to filter out as much stuff anymore. And so I like that idea of running through to see, maybe it improves it after doing it 2 or 3 times, but maybe after a certain period of time, you're not getting any difference. So that would be pretty neat too, to see.
Yeah, I think we'll actually see a very similar thing here. when you think about our materials, I noticed I put in a lot of cotton balls, but as I pass through the liquid, it's going to effectively saturate, just like Lyle had suggested. So maybe I need to replace my materials. But of course, if each time I have to replace my materials, I'm introducing more cost, and that can make things pretty difficult too.
Let's see. Someone wants to see. Can we repeat it? Why don't?
Yeah.
Why don't we? You've got a. Let me see if I can get a second cup here. You want to? This way we can.
Without spilling. So I'm going to take my old dirty water per the earlier suggestion. I'm going to try to catch it really quick. And now we are passing through a second time here.
And one thing you can do if you are doing this and want to compare results is you can actually take pictures and compare the color or the clarity of the water from one experiment to another, and then you can see those comparisons. Because looking at this, I don't remember what it looked like when he first poured it in. So it's hard for me to remember, oh, that's clearer or it's darker, or I just don't remember. But if you can take photos of it, then you have that visual reminder.
Especially if you're in a classroom and, I love teaching science and I like making my kids write lab reports. That makes a great figure for you guys to include in your data. So that's pretty nice. I don't know, Lyle, maybe a little bit better.
A little bit, yeah.
I'll note that I think much like we were concerned about, I think I have less in here than I did originally. So I think I've lost some more water into my filter, which means my yield, the amount of drinkable water I could even possibly get, has been reduced. So maybe it gets a little cleaner, but I am losing the amount of drinking water I can get. So another kind of trade-off.
Yeah. One of the questions is about doing or adding another material. And this was sort of what we had talked about earlier in terms of repeating the cycle. We don't quite have the space to sort of pull these apart and recreate to get them working slightly different as a different iteration. But that's something we encourage you to do, to see if the first design you come up with when you make a single change, is it better or worse? And that's why I said a single change, because if you make 3 changes and your filter is worse, you're not necessarily sure which one of those changes made it worse. So as Brandon mentioned, being good scientists, we want to make that single variable, change that one thing, and then we can see what's really making a difference. Is it getting better or is it getting worse?
Yeah, what we're really referring to is a process of optimization, right? And you have to imagine that in the real world, scientists and engineers would do exactly what you've described. They would run this through a single kind of material and take a look at what effect that had, and then another one, and another one, instead of moving right into a combination just like we did.
Let's see, other questions?
Oh, wow. So I see the question from Nathan in Puerto Rico. So how does the system, the ECLIS system on the ISS actually do water filtration?
There's a couple different processes, and I'm not super familiar with all of them, but I know that the very first thing they do, and I'll talk about the urine, is they capture the urine in a container and they spin it, because again, there's no gravity in space. And so when they spin it, that force, that rotational force, pushes it against the walls of the container. Then they heat that urine, and the heat evaporates the water out of that, and it removes or it leaves behind a solid waste. So they're capturing the water vapor that gets evaporated from that. And then that water vapor is then filtered. I think they have reverse osmosis, and I forget some of the other ones, but there's quite a big process. The device that does it, I showed you the picture, it's probably 5 refrigerators wide, and 2 or 3 of those units are 2 of those refrigerator size units are just for purifying water. So that's how they start with that process. But again, they have to remove those solids, and here on Earth, we can just let gravity remove a lot of solids, but in space, they've got to do a lot of spinning to remove some of those solids. And I'll put the picture back up, and you can see some of the cylinders in there, give you an idea of some of those rotational pieces that spin to get that force to separate.
I'll add, here on Earth, again, we do very similar technology, although, perhaps not as specialized as it is on the International Space Station. But maybe you guys have heard of words like desalinization or reverse osmosis. So because the salt in the water has a charge, right, is electrically conductive, you can actually use power. You can use electricity to be able to pull some of those salts out as well. So it's not just a physical separation, like we talked about with the vinegar. How do you get other chemicals out, or perhaps things that are dissolved? Filtering out the water, if something is dissolved, it doesn't actually take it out. That's why we have this brown water here at the bottom. So what is it that we can do to change the chemical structure as well to be able to really clean this water?
Well, do you have any questions on yours that are?
No, I think we're ready to wrap up.
All right. Well, I'll say, as a scientist, I was very careful about not just grabbing things because I'm getting thirsty right now after talking, and I see all these cups around me. But just a reminder as you're doing this, make sure you know what your water bottle is and what your filter bottle is as you're doing these activities. So I'd like to say thanks for joining us today. We really appreciate your questions and your time today. Hopefully you will have a good opportunity to build your own filters. And Brandon, anything else you wanted to add before we wrap up?
Nope, just thanks again for all of your time and joining us. And again, teachers and parents at home, I hope you guys have enjoyed this activity. Keep an eye on the JPL Education website for future workshops just like this one.
Bye, everyone.